Welcome to our brief discussion on the derivatives of logarithmic functions, with an even briefer discussion at the end on e and how we get it from limits. Okay, if you're not familiar with what a log function looks like, you should at least make yourself somewhat familiar with it. Understand the graph is the easiest way. You know that a log function is an inverse of an exponential function, and therefore if you know something about the exponential functions, you know something about the log functions, and vice versa. So for instance, if you remember that your exponential function gets really close to the x-axis as you go out to negative infinity, it goes through the point 0, 1, right, and then grows rather rapidly. Well, because it goes through the point 0, 1, the inverse function has to go through the point 1, 0. This one gets asymptotically close to the x, so this one gets asymptotically close to the y, right? And basically what's happening is when you have inverses, they are mirror images over the line y equals x. So this black line represents log base 10, right? Then you got log base 5, log base 3, log base 2, and of course log base e, which is the natural log, is 2.7. It's going to be right in between these two, still going through that point. All right, so basics of log functions. Taking the derivative of the natural log function, remember it's just log base e. It's very simple. It's 1 over x. But instead of trying to memorize all of these formulas, the best one to kind of commit to memory is this one, because that's the most generalized function. You're now just taking the natural log of a function. And if you take the derivative of natural log of a function, you know it's going to be 1 over that function times the derivative of that function. So basically the derivative of the function over itself. And this nice little easy ratio here is the best way to remember it. Because then when you think about natural log of x, well, it's just the derivative of x over x. And the derivative of x, of course, is 1. Okay? So that's what I suggest is you kind of zone in on that one. Here's a simple example, taking the derivative of the natural log of sine of x. So now sine of x is our function. And if we remember our formula, it's just the derivative of sine over sine. And of course, that's where we get cosine over sine, and the final answer is cotangent. Now you might be asking yourself, why bother? You know, what's the point? Well, log functions model a lot of things in the natural world. The pH scale is a very common version of a log function. Sound waves, there's a scale for sound that's a log scale as well. So it comes up quite a bit. But another nice application of the log function is you can use logarithmic differentiation to take derivatives of very complicated functions. Here's an example of that. So we have y of all of this stuff, and we go, ooh, that's just ugly. I don't want to have to deal with that. If we had to do it as it sits, we would have to use the quotient rule and the product rule, right? Because we have 3 pieces. One function times another function divided by a third function, right? So, you know, we think of this as f, g, and h. And so the quotient rule, we'd have to do the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. And when we take the derivative of the top, we'd have to use the product rule and do derivative of the first times the second plus derivative of the second times the first. And this is just going to become this big, long, ugly looking algebraic expression. Big pain in the butt. It's a lot easier, however, if we just take natural logs of both sides. Because taking the natural log of both sides is a legal move, right? The two things are still equivalent. In fact, doing logarithmic transformations, which is basically what you're doing when you take a log of both sides, is a very common thing that's done in statistics as well, If you have data that is not of the form that you like, you can take a logarithmic transformation of your data, and then all of a sudden it'll fit a regression equation better, and you'll be able to do other things with it. So it's a very common technique to take a log of both sides. In this case, by taking the log of both sides, we get to avail ourselves of all of those wonderful logarithm rules that allow us to take a complicated expression and drastically simplify it. Because remember, if we take the natural log of x to the 3/4 is just 3/4 natural log of x. Right? Whenever you take the natural log of something to a power, the power comes down in front. And then there's also that nice rule that if you have the natural log of x times y, it's the natural log of x plus the natural log of y. So this product is just going to become the sum of two natural logs. And then we also have the rule, the natural log of x over y. If you don't remember, you can look these up, or I'll tell you right now. Natural log of x minus natural log of y. Remember, so a product becomes a sum, and a quotient, right, division, becomes a difference. And when you combine all of these rules together, this big ugly thing simplifies to this. This is your yellow piece, simplified, right? This is the green piece, simplified. And here is the purple piece, simplified. You get the plus and the minus from the rules of quotients and products. And then the powers, right? Remember, this is to the 1/2 power, a square root. Powers just come down in front. 3/4 natural log of x, 1/2 natural log of x squared plus 1, minus 5 natural log of 3x plus 2. And we're good to go. Now we can take the derivative of this whole thing, and because these things are separated by pluses and minuses, then we get to just take the derivative of the first piece plus the derivative of the second piece minus the derivative of the third piece, and we don't have to worry about the product rule, the quotient rule, anything. We just have to do this simple derivative of logs of things, right? In this case it's a natural log, but it's still just a log of something, and we use that the derivative, right, of log of f of x is just its derivative over itself. So for the first one, 3/4 natural log of x, well, that's just 1, right, because the derivative of x is 1 over x. 1/2 natural log of this, well, the derivative of this is 2x over itself, so there's the 2x over itself. All right, so there's our first piece. Second one becomes this one. And then the last one, minus 5, and then it's just the derivative of this, which is 3 over itself, and there's that piece. And we still have to do the derivative on the left-hand side, right? So the derivative of natural log of y becomes 1 over y, and then don't forget the dy dx, because remember, we're taking derivatives with respect to x. So it uses a little implicit differentiation here. We have to remember that when we're taking the derivative of y with respect to x, we treat it like x and then slap that dy dx on the end of it. Okay, to solve for dy dx, all we had to do was multiply both sides by y, and there we have it. And because the original function explicitly expressed y as a function of x, we can sub that back in, and now we can finally list our answer all in terms of x's. And that's really how we would want to leave it. You could distribute it out, and then it's just going to get really ugly. You might as well leave it like this, because the better thing is to have it factored, because if you want to figure out when it equals 0, then you can set each of those factors equal to 0 and then go from there. So it's better to leave it factored. Okay, so logs can help simplify your life if you're trying to take derivatives of very ugly functions. And that's pretty much all we need to know about logarithmic functions and taking derivatives of natural log or of logarithmic functions. The next section we're going to talk about, here's just the basic steps in doing logarithmic differentiation, which we've already seen. right? You take the natural log of both sides. Why the natural log of both sides? It really doesn't matter. You could take log base 10 of both sides or log base 5 of both sides. It really doesn't matter. We just take natural log because it's the most common one we're used to. It's the easiest one to write. There's really no reason why you have to take any type of a different base. But natural log is the best one to do. Differentiate it implicitly with respect to x and then solve the resulting equation for y prime, which remember is the same thing as dy dx. And then just a little reminder of the power rule since you're going to be using that a lot. Okay, this last little bit, these last 4 slides, we're just going to talk briefly about where e comes from. We can remind ourselves that if f of x equals the natural log of x, then the derivative is 1 over x. And therefore, the derivative evaluated at 1 equals 1. And we can now use this fact to express the number e as a limit. So all we're going to be talking about here is kind of where e comes from. So from the definition of a derivative written as a limit, we know that the derivative of the function at 1 is equal to the limit as h approaches 0 of the function evaluated at 1 plus h minus the function evaluated at 1 all over h, which is the same thing as saying take the limit as x approaches 0 of 1 plus x. All we did was swap out x's for h. Okay, in the next step, all we're doing is we're actually applying this to this function, f of x equals natural log of x. And then we get natural log of 1 plus x minus natural log of 1 all over x. We factor out that x on the bottom and just make it 1 over x times the top, but natural log of 1 equals 0, so that's why that just goes away, and when you say times the top, you're just left with natural log of 1 plus x. Okay, but by rules of exponents, 1 over x times natural log of 1 plus x is the same thing as natural log of 1 plus x raised to that power. So that's all we're doing here, right? We evaluated this and it equals 0. Then we took this back up to a power to get to here. Okay, so far all we did was some basic manipulations with the rules of natural logs. Okay, because f prime equals 1, then we know that the limit of that stuff also equals 1, because we saw from the previous slide that the derivative evaluated at 1 equals that stuff. So if a equals b and b equals c, then by the transitive theory, a equals c. And we have that the limit as x approaches 0 of natural log of 1 plus x all to the 1 over x power has to equal 1. Okay, then by the continuity of the exponential function, we know that we can do e to both sides, right? We can do, if those two things are equal, then we can say e raised to the stuff on the left has to be equal to e raised to the stuff on the right. So e to the 1 has to equal e to all of that other junk. Well, e to the 1 just equals e, right? So if we did e to this stuff and e to this stuff, we just get e here. And on the left-hand side, we get e raised to all of this. We can take the limit outside, and it's just e raised to all of this stuff. And then e raised to the natural log of some stuff. The e and the natural log cancel each other out, and now we get e equals the limit of 1 plus x, right? As x goes to 0, of 1 plus x to the 1 over x, and there we have the definition of what e is. So that's how e was defined. Here's an illustration of the function 1 plus x raised to the 1 over x and a table of small values. Remember, this is not the function e to the x. This is supposed to just represent e, a number. So as x is going out and out and out to the right, we can see that the function is leveling itself off. It's getting lower and lower, but it seems to have a floor. And those numbers seem to be approaching 2.71 something something something. And in fact, if you take it out far enough, you get 2.718, 2818, and it goes on from there. If we sub in n for 1 over x, then if you don't remember it, right here, limit as x goes to 0 of 1 plus x to the 1 over x, becomes the limit as n goes to infinity of 1 plus 1 over n to n. This is another way of writing the same thing, right? It's just another way of expressing e. We just know that as x goes to 0, that's the same thing, from 1 over x. So because of this, because n equals 1 over x, as x goes to 0, we can see that this goes to infinity. So now when we talk about the limit in terms of n, it's going to infinity instead of 0. And then instead of 1 over x, right, if n equals 1 over x, then this is where we get, right, if n equals 1 over x, then multiply both sides, xn equals 1, or x equals 1 over n. That's where that substitution comes from. And then of course it was raised to the 1, right, because originally it was 1 plus x. And then the original power was 1 over x, which now just equals n. So all we did was some algebraic substitutions, manipulations. And there is the other definition of an e. So those are the two different ways that e is defined, with n's and with x's. Normally n is when we're in the financial and economics world, they tend to use n's, and when we're in the calculus, more math-based world, we use x's. And that's everything, guys.